Good morning. Good morning. We're continuing our talk on preliminary topics. Following units and following scientific notation, we're now moving into scalars and vectors, whatever they are. Scalars. Scalars are numbers. Well, actually, that's not entirely true. Scalar quantities are numbers, are quantities that can be specified just using a single number. A single number on its own is sufficient to specify mass, length, and time. A single number would be also sufficient to represent temperature. Distance. Well, of course, that's just the same as length. If we were doing it, electric charge later on. And there are many other things specifiable by numbers. When we get to doing vectors, a very important scalar quantity is the magnitude of a vector itself. These are quantities specifiable by vectors. Quantities that are specifiable by scalars. Quantities specifiable by vectors, whatever they are coming up. First of all, what is a vector? There are many different ways of looking at a vector. There are very rigorous mathematical definitions of a vector. For us, this is what a vector is going to be. Vectors are mathematical devices that keep track of components. That means there are parts to the quantity that we're studying. For example, how far north did you go versus how far west did you go? There's a northern component and a western component. An example, something that keeps track of components. We can have in a bag of fruit, we can have 3 apples in it, 2 pears in it, 6 lemons in it. Okay? We can represent that by the vector 3 with the small a with a little hat over it, and a p and a squiggle underneath it sometimes, with the 2 in front of it for the pears, and 6 lemons. And we can also represent it in a different way, with a plus sign in between. Either one of these are acceptable notations, standard notations. Even this one is often used. There's a slot for the apples, a slot for the pears, and a slot for the lemons. So therefore then, if I had 2 bags, let's say 3 bags actually. The whole thing about vectors is you can add them all up. You can't add apples and pears. Well, you kind of could. You could say in this bag here there are 7 pieces of fruit. In this bag here there are 14 pieces of fruit. In this bag here there are 2 pieces of fruit. But we want to keep track of the components separately. Well, the whole idea of vectors is it allows us to do that. We keep track of all the apples. 4 and 0 and 0 is still 4 apples. 2 and 10 is 12 pears. 1 and 4 and 5 and 2 is 7 lemons. Now sometimes people put plus signs in there. Now, the result of adding three vectors that is called the resultant, actually. And this resultant is a new vector, consisting of having added up all the whole component. Now, a vector can be used to represent many things. It could be used to represent, let's say, a 100-dimensional vector. It could be a portfolio on the stock market. Somebody's portfolio would have 100 slots in it, let's say, for each different investment. Most of us, most of the vectors we'll be dealing with will be just two-dimensional. In other words, just these two parts. We'll talk about that later. We'll simplify this. This is a general discussion. Okay, so what kind of physical quantities will be representable by components? Okay, so if we have displacement is one. Displacement. We could, let's say, travel 6 miles north and 2 miles east. The resultant is this vector. I could carry on the motion, call this D1. I could head south, right? The reverse of going north would be going south. So therefore, let's say -3 north. And I could head west, not east. That would be -2 steps. So let's see what that looks like. Well, I go south by 3, and then over again, and I have a new vector. And here's where it ends up. Look, watch this. +2 and -2 is 0. That's exactly what we have. We haven't gone east at all. +6 and -3 is +3 north. So we end up 3 units north, just half the distance. Vectors worked out very neatly. You can add up vectors in any order. Now this is, as you know, the associative rule for adding vectors. What physical quantities are representable with vectors? Well, we see that the first one is displacement. Moving an object around the place is displacing it. Now, we don't say the following quantities are vectors. Actually, people say that all the time, but it's not correct. Well, obviously, displacement has components. We have a northerly and an easterly motion component here for displacing stuff. The next one is velocity. Velocity is related to speed. Now when we get into our terminology and we start doing kinematics, we will say that speed, we're just calling it here for the record, will be the magnitude of the velocity vector. Speed and velocity will not be the same thing. Velocity is a vector. Speed, which we represent like that, we don't use this vector notation. Speed, v, little v for velocity 2, is just something quantifiable with a number. For example, 3 meters per second. We'll talk about that later. The other quantities we will study in this course representable by vectors are momentum. Momentum P. Force F. Angular momentum L. And what will be called torque later on. Okay? We have nothing else. Displacement, velocity, momentum, force, angular momentum, and torque are our vector quantities in this course. Now we look at a special kind of vector, the unit vector. The unit vector is a vector of unit length, of length 1. Well, we would use just this term. A special vector is the position vector. It locates the particle. So now we're going to put our vectors on a coordinate system. Our coordinate system will be the Cartesian system. Now let's look at a particle located at the point 3, 4. So there is a particle located at that point. Its position vector is a vector that begins at the origin and ends up at that point. It's often used, the letter R is often used to denote the position vector. Now the little hat above, the little squiggle down here in our course denotes vector. The little hat above it denotes a unit vector. Because I is traditionally used to denote a unit vector in the x direction. Now what is the length of this line here? Well, we use Pythagoras' theorem. In this case here, The square root of 3 squared plus 4 squared is the square root of 25, which is 5. So it's a 3, 4, 5 triangle. 5 is the length of that vector. So we'll say that the magnitude or the length of this vector R is 5. Now 5 is a scalar. A minute ago we said a very important vector is the length of a vector, the magnitude of a vector. This is the magnitude of this position vector. It is 5 units in length. Now we want to construct a unit vector. What we want to do is make a vector in this direction whose length is 1 unit. That's a unit vector. Well, we take this vector and we divide by its magnitude. Divide this vector of length 5, right, by 5, and we get 1. So let's say the magnitude of this guy is 1. Now let's see that that's the case. The magnitude is always found by taking the components and squaring them. Yeah? And taking the square root. Okay, so let's do that. Well, we get 9 over 25 plus 16 over 5. And of course 25 over 25 is 1. So far now we've seen the unit vector, we've seen the idea of the components, we've seen how to find the magnitude of a vector. Let's summarize that. To add vectors, we add the components. When we add the vectors, we get the resultant. Addition of vectors is associative. Now I'll add a third unit vector. This would be in the z direction. The Vy is the component of this vector in the y or j direction. The Vx is the component, these are scalars, and this could be a velocity, for example, and this is the magnitude. Square the components and take their square root. It's a generalized Pythagoras' theorem. Doesn't matter how many, you could have 20-dimensional vectors, you still carry out the same rule. Now, R is the unit vector in the direction of the position vector. And then the direction of the vector R, a unit vector in that direction is take the same vector and divide by its magnitude. We could add a third direction. We could add a third direction like that. Okay, so we're starting on vectors and we will continue with more vectors for the next session.